Hello everyone, I hope you're doing well. So in today's lecture, we're going to be talking about the branch and bound method for solving integer programming problems or mixed integer programming problems. And this is a method that's been used for many decades in attempting to solve large instances of these models. As I mentioned, IPs, they require much more computational power than simple linear programming models. And that is because at each one of those integer programming problems, we are solving a series of linear programming relaxations of that model. So in this lecture, we're going to go over about the steps that are necessary to perform in order to run the branch and bound algorithm and solve those problems. Then, after applying the branch and bound, we're going to try to find what are optimal solutions to this integer programming or mixed integer programming models. Okay. Last class, we were looking at an optimization problem that had the following characteristics. So suppose that we are maximizing the summation over j of cj times xj, and then that this model would be subjected to a set of constraints that look like this. So summation of j equal to 1 up to n of aij xj. This should be less than or equal to bi. And then this is for all I equal to 1 to up to m. And then we would have bounds that would look like this. So xj is greater than or equal to a lower bound that in some cases are valued at 0, and an upper bound less than or equal to an upper bound uj here. For any j, that is equal to 1 up to n here. This, the way it is represented now, is just a linear programming, but we know that we're looking at integer programming models, so we need to have the requirement that all the xj, they should be integer. So xj is integer for all j that belongs to the set j that's contained in 1 up to n, right? So in this case, we have a model that has any variables, and we have m constraints, right? Where n here is the dimension of the decision vector, and m is the dimension of the number of constraints that I have in my problem. So, as we look at this problem, this is a maximization, and the only set of decision variables that I have is x. So I'm maximizing to try to obtain the objective function value for a specific combination of the decision vector, right? So we wanted to pick the decision vector in such a way that it will satisfy all the constraints of this feasible region and also satisfies the integrality requirement of the integer programming. So this is an integer programming model. So now we look at that last class in a way that we could solve this problem as a linear programming. And if we're solving this problem as a linear programming, we have what is called an LP relaxation of this original model. The LP relaxation of the integer programming, it discards the integrality assumption. of the IP, right, of the integer programming model. So when we solve this problem as an LP, the decision vector x here, it will be represented as a continuous vector, right? Continuous, it can have any of the elements of that vector can have a continuous value, right? So that means, for example, that x can be equal to x1 can be equal to 10.57, right? So this is a real number, and it would be okay for us to have a solution for that, like that, for an LP relaxation. On the other hand, if we are considering that this is an integer programming model, x in this case, x1, right, the example that I'm giving, it had to be either 10 or 11, right, to represent that integer number. But the process to get to 10 or 11 follows a specific algorithm that will help us to determine what are the values not only for x1, but for all the elements of my decision vector x. So this algorithm will try to find the values for x that will help us to satisfy all the constraints of my model, as well as the integrality assumption for the decision variables. There are different algorithms that do that in integer programming. We're going to look at one of the classical methods that's called the branch and bound method. So the branch and bound. For the branch and bound, we will use some notation, and this notation states that we'll have the representation of the floor operator. So the floor operator of the decision vector x will denote here, this will denote the floor operator. So this floor operator means that we will round down the value of x. What does that mean? That means, for example, that if we have x equal to the 10, x1 equal to 10.57, that means that the floor operator of x1 will give me a value that's 10, right? So that's what we get out of that floor operator. On the other hand, suppose that x2 is equal to, 11.93, right? What is the floor operator? What is the result after I apply the floor operator to x2? That's basically 11, right? It doesn't matter what is after the dot or the decimal, right? We will neglect this and we'll take only the integer value. So that means that x2 after the floor operator will give me 11, right? The same thing would be true if we have, for example, x3 equal to 5.05, and I apply the floor operator. The floor operator to x3 will give me a 5, okay? So this concept of the floor operator is key when we're solving an integer programming using the branch and bound method. Okay, also, if we have, for example, let's say that x4 is equal to negative 2.3, right? What is the result after I apply the floor operator to x4? So in that case, the floor operator will give me minus 3, right? Because we are rounding down, always rounding down. And in that case, the negative 2/3, the rounding down means going back to negative 3 instead of going up to negative 2. Okay? So with that out of the way, with this notation, we can start to define some steps for the branch and bound algorithm. And we're going to see that next. Okay, branch and bound algorithm. So in the step 0 here, I'm going to initialize the algorithm. So we're going to select an error that should be greater than or equal to 0 as the desired tolerance level. So we're also going to define z star as negative infinity. Okay, so this would be the solution for the integer programming model so far. So as we're maximizing, we're just setting that the value that I have right now is negative infinity, right? And we wanted to improve on that objective function value. So as I did that, I'm gonna then solve the LP relaxation of the model above, right? The model that we're looking at, that was an integer programming model. So we will relax that assumption of the integrality of the decision variables. And we're gonna solve this LP relaxation in order to obtain the solution out of that LP relaxation associated with the decision vector and the objective function value defined as the ZLP. If the LP relaxation is infeasible, it means that we were not able to find a solution, right, for that LP relaxation. So if we don't have a solution for the LP relaxation, this means that we also don't have a solution for the IP, or the integer programming model. So in this case, when the solution for the LP relaxation is we cannot find it, it's an infeasible problem, it means that also the integer programming is infeasible and we can stop the algorithm, right? There is no solution for that integer programming model formulation. However, if we were able to solve that LP relaxation and find a solution for the objective function defining all the elements of the decision vector, right? If this solution, right, if this decision vector for all the elements, they are integer, that means that we were able to find the solution. We were able to find the solution for the integer programming. And because we were able to find the solution for the integer programming, we can stop the algorithm. And in this case, we would say that here, the Z for the integer programming, or the optimal solution there for the objective function, would be equal to the solution for the linear programming, and the decision vector would be exactly the value associated to the linear programming model that we got. Again, so if we solve that LP relaxation and we're able to find the decision vector in a way that all the components associated to that decision vector, they are integer valued, it means that we are also able to find the solution for the integer programming and we can stop. Okay? So if we don't stop, if that's not the case, we will go to step 1. Then label the current LP, linear programming model, as an unphathom subproblem. We're going to see this more in detail as we solve the example later on. Then we start if we didn't stop at step 0, we'll start the step 1 of the algorithm. And the step 1 of the algorithm is called branching. Here, in the branching, we're going to select an unphathom subproblem. And then, in this unphathom subproblem, we will select an element of that decision vector from the LP relaxation result, such that this element is a fractional one. What does that mean? That means, for example, that I have an x2 there that's equal to 2.5, right? So this is a fractional value, and it means that the LP relaxation gave me a solution that's not integer, and I wanted to make this element integer valued. Okay? So, with that selection of the element of the decision vector that is fractional, we're going to create 2 new subproblems. And this subproblem will go more or less in this direction, right? So suppose that this is the original LP relaxation that I solved. I found the XLP and I found the ZLP. So in that node, we're going to create a branch, and from that branch we'll have another node that will represent another optimization problem, and one more to the right side here that will represent a different optimization problem. To the optimization problem of the left, we will add a constraint that will look like x of j is less than or equal to the floor operator associated to that element. And in the right branch of that original node, I'm going to add a constraint to that original model that will be going to be xj is greater than or equal to the floor operator xj of the LP plus 1. What does that mean with respect to that 2.5, for example, right? It means, for example, that I solved this LP and it gave me a z, right, zLP, and gave me a value for the decision vector, the element number 2, that was 2.5. That means that here, on this node that I'm going to label node A will be the original LP that I had in my node I here, my initial node, with the addition of a constraint that looks like x2 is less than or equal to the floor operator applied to 2.5. That's basically 2, right? So this model A here will be original LP plus the new constraint x2 less than or equal to 2, right? On the other hand, the problem associated with the letter B here will be the original LP plus the new constraint x2 greater than or equal to 2 plus 1. So that means x2 greater than or equal to 3, right? Defining this in a more general manner, we will create these two new subproblems by adding the respective constraints. So to the left, we will add a constraint that says that xj is less than or equal to the floor operator of xj LP, and xj greater than or equal to the floor operator applied to that element of the decision vector from the original LP plus 1, right? Where here j is one specific index of the decision vector that we decide to branch on. Okay? With that, we conclude the first step that was called the branching step, right? So now we go to the second step of the branch and bound algorithm. And in the second step is called the bounding step. So in this step, with the new constraints, we're gonna solve the new LP relaxations of the two new subproblems, and for each of them, we will obtain the solution to that relaxation with the addition of a new constraint and the values of the decision vector represented by that LP relaxation with the new constraint. Or we discover if that new relaxation is infeasible. So now we go to the step 3 of the algorithm. And step 3, it is called the fathoming step. So here, for each subproblem that we declared in the previous step, we will define that it will be fathom if one of the tests below are satisfied. In other words, we're going to have 3 tests. If one of them is checked, if the the analysis that we do, that test is satisfied, then we have to fathom that subproblem. And for this, we have the test 1 here that says that a better solution exists. So in test 1, we're going to see if the solution for the LP that we are solving right now with that specific subproblem is less than or equal to the incumbent solution that I have for the integer programming. So again, here this Z denotes the incumbent solution to the IP. And this solution is integer value. In this case, we will fathom that subproblem. What does that mean? For example, suppose that we solved this LP, and we have the solution for that LP, and we have the objective function value. However, that LP, it gave us a value that was 13.5, right? This LP came from a branch that I have an incumbent solution that was found at some other place on my tree that gave me that the ZIP at that moment, or the incumbent solution up to that point, was equal to 12. Okay? Because I got this ZLP that's 13.5 in this branch, I'm solving that new relaxation with the additional constraint. And now suppose that I get a ZLP that is equal to 11.5, right? So as 11.5 is lesser than my incumbent solution 12, I can stop this tree right here. I can fathom this node. That means that it will not continue below, right? Because my incumbent solution is already better than the solution that I can obtain in that branch through that LP relaxation. Meaning that all the subproblems that I would have below would give us a solution that's worse than this one. Okay? So that's test 1. Then we have test 2. The test 2 is we're checking for infeasibility, to see if the problem is infeasible. If this LP relaxation is infeasible, we will fathom the node. What does that mean? For example, we're coming from this branch. We added this specific constraint here that says, let's say that x2 should be less than or equal to 2. And when I'm solving this specific LP relaxation, I found no solution, right? This is infeasible. So that means that, again, I'm gonna fathom that node and I can stop that branch and I will go to the next branch, right? So I will not continue this tree below here, right, from that side. The third test is if we find an integer solution. So this test here, if the solution for the decision vector associated with a particular node for all the elements that are inside that decision vector are integer, then we can fathom that node. That means we will not continue in that tree, on that branch of the tree anymore. And if the solution to that particular LP relaxation is greater than the incumbent solution, what I'm going to do is I'm going to say that my new incumbent solution will receive the information that I just obtained with that LP relaxation, that for the decision vector, as well as for my integer programming solution. Right? So means that the incumbent solution is for the decision vector is equal to the current solution that I found for the LP relaxation, because they are all of integer value, and it means that my objective function value is the same that I got from my LP relaxation. And this will become the new incumbent solution. We will reapply then the test 1 to all unfathom subproblem. Then we go to the last step of the branch and bound algorithm, step 4, that is called terminating. So here on this step, if all the nodes that I have in my tree are fathom and the objective function value of the IP continues to be minus infinity, we will stop and say that the integer programming, or the mixed integer programming, if we're solving mixed integer programming, is infeasible. Otherwise, what we're going to say is that we'll let z bar be the maximum of the solutions of the LP relaxations across all the unfathomed problems. Then if z bar minus z star, that's the incumbent solution for the IP, is less than or equal to an error times that incumbent solution, we will stop also the algorithm and say that the incumbent solution for the decision vector is a solution within the error term times 100, right, of the optimal solution. If this is not the case, we repeat. Okay? So this concludes all the steps of the branch and bound algorithm, and we're going to see how it works with a problem example next. So for this example, we're going to work with that problem that I introduced last class. So this is a maximization of 4x1 minus 2x2 plus 7x3 minus x4, and we are subjected to 4 constraints. First one says that x1 plus 5x3 should be less than or equal to 10. The second one says that x1 plus x2 minus x3 should be less than or equal to 1. The third one is 6x1 minus 5x2 less than or equal to 0. And the last one is x1 plus 2x3 minus 2x4 should be less than or equal to 3. And in this case, all my decision variables should be greater than or equal to 0, right? The non-negativity constraint. And all x1 up to x4 should be integer value. Okay, so to start the branch and bound method, we create the first node in that tree. And at that time we will have that the incumbent solution is empty, right? We don't have anything there. And our objective function value, the incumbent one, receives minus infinity, right? So at this particular node that I'm going to label it as node A, I will have to solve that original problem in its LP relaxation, right? So I want to find out what is the ZLP and the XLP. And we're going to see how to do that using Pyomo. Okay, so we are looking at that problem where the objective function is the maximization of 4x1 minus 2x2 plus 7x3 minus x4, and we are subjected to those 4 constraints that we just described, right? So this is an LP relaxation of that problem. As you can see here, we have the decision variables to be represented as reals, so that means that it can have fractional values, right? So when we go to our Python console and we solve that problem, we get the solution for the objective function as 14.25, and we get the values for the decision variables x1 as 1.25, x2 equal to 1.5, x3 equal to 1.75, and x4 equal to 0. You see that all these decision variables are fractional, right? x1 through x3. x4 is 0. So I'm going to write here in this node that the value for my LP relaxation, the objective function value, is equal to 14.25. And I have that x1, x2, and x3, they are equal to 1.25, 1.5, and 1.75, x4 equal to 0, right? This is the value of the LP relaxation. So now what we will have is we need to branch on that node, right? And we need to branch with respect to a specific variable that's fractional. So we have 3 variables here that are fractional. So x1 and x2 and x3. Which one we're going to choose? We're going to choose the one that has the highest or the largest fractional value. So larger fractional value. And in this case is x3, right? So x3 has the larger fractional value. So let's move this a little bit there. So in this case, we're going to create a constraint on this branch that says that x3 here should be less than or equal to the floor operator of 1.75. In this case, x3 less than or equal to 1. And in the other branch, we'll have a node that says that x3 should be greater than or equal to the floor operator of 1.75 plus 1. So 1 plus 1, that's 2, right? So I'm going to label these nodes B and C. Okay, so now we want to solve that subproblem B, right? So in order to solve that subproblem B, we need to add a new constraint that says that this new constraint M that I'm going to call constraint 5 here is equal to a constraint, and this constraint has an expression that is equal to model dot x3, that's the decision variable that I want to add that constraint, should be less than or equal to 1. Right? So now I'll save this and I can rerun that that optimization model. And I have now that the solution for this linear programming is 8.45, and the decision variable value is 0.99 for x1, 1.0909 for x2, 1 for x3, and 0 for x4. So now we go here and we say, hey, the ZLP for this guy here is equal to 8.45, 5.4545, and the solution for the decision variable values are x1 equal to 0.909, x2 equal to 1.0909, x3 equal to 1, x4 equal to 0. Right? And then on the other hand, we need to figure out what's the solution for this other node C, right? So this node C is the original LP relaxation with the addition of this new constraint x3 greater than or equal to 2. So let's look at that. So in order to represent that subproblem C, we're going to change this constraint to be x3 greater than or equal to 2. We're going to save it, and we're going to rerun that Python script. So now you see that the objective function value is 13.5, and the decision variables are 0, 0, 2, and 0.5 for x1 up to x4 respectively. So going back here, the solution for this LP give us 13.5, and x1, x2, x3, and x4, they're all equal to the values that we just went over. So 0, 0, 2, and 0.5. Right? We were not able to find an integer solution yet. However, the most promising path is through node C that give us an LP relaxation value of 13.5, while the LP relaxation of node B give us an LP relaxation with optimal solution of 8.4545. So we're going to branch in this direction here, and we will continue, right? So that means that we're going to create a node D here and a node E, where node D will have a constraint that says that x4 should be less than or equal to 0, right? The floor operator applied to 0.5. And node D will have a constraint that says that x4 has to be greater than or equal to 1. Again, this is nodes D and E. So now we're going to solve those linear programming relaxation associated to node D and node E. Okay, so now to solve the subproblem D, we need to add a new constraint that we're going to call constraint 6. So this is a constraint that has an expression, and this expression is equal to the decision variable x4 should be less than or equal to 0. We'll save this, we'll go back to Python and run it, and we were able to find no value for our problem, right? It's saying that our model is an infeasible problem. So we saw that this problem is infeasible. And that means that we can fathom that node and we don't need to continue it below, right? Because we're not able to find a solution for the LP relaxation. That means that we also cannot find a solution for the integer programming problem. Now we go to node E. So we saw that node D was infeasible, so it could be fathomed. However, we can solve now node E and see if we can find a solution for node E. In that case, we have to add a new constraint. That's constraint 6. So this new constraint is again an expression where the decision variable x4, it should be greater than or equal to 1. So we'll save that, go to the terminal, run that Python script, and voila. Now we are able to find a solution that gives us a z value of 13, and all the decision variable values are integer valued, right? So x1 equal to 0, x2 equal to 0, x3 equal to 2, and x4 equal to 1, sorry. So now we're able to find that all the decision variables have integer values. So x1 0, x2 0, x3 2, and x4 equal to 1. So as you could see, now for node E, we are able to find a solution for the LP relaxation that gave us an objective function value of 13, and with x1 up to x4, all integer valued, right? So that means that x1 was 0, x2 0, x3 was 2, and x4 was 1. As we look at the other nodes of the tree, this one we can fathom because we were able to find a solution that was integer. And this solution will update my incumbent and say that my incumbent solution now is 13, with my decision vector being represented as 0, 0, 2, 1, 1, that are just the solution from this node, right? As I look at the other nodes in my tree, I still have node B that I could continue, but as we have an LP relaxation value that is lesser than my current incumbent integer programming solution, I can also fathom that node. And then here, I finally can stop and say that the optimal solution for the IP was 13, with the decision variable values equal to 0, 0, 2, and 1. So this is how we apply the branch and bound method for this problem.